Okay, let's start today's lecture. We will first briefly review last lecture's material on MDP planning. I introduced the start of the MDP planning section last time. So, reinforcement learning. The goal is to find the optimal policy given the reward function. So the agent is trying to maximize its cumulative reward. That is, so this is the cumulative reward. Every time step it gets a reward a small RT, and you sum up the reward in the future horizon 0 to T. That's your cumulative reward. So you're not just maximizing the current reward at the current time step. You are really concerned about a cumulative reward in the future horizon. And the environment is a Markov decision process. There are two types of IR algorithms. One is model-based, one is model-free. Model-based is when you have the MDP of the environment. You know how the environment behaves. Given the current state S and action A, the environment will give you back a reward and next state in the form of probability distributions. So the environment is not deterministic in general. So if you know the MDP, you can perform planning with either value iteration or policy iteration. For model-free IR, you may have two variants. One is value-based and one is policy-based. So value-based methods learn the value function V or Q and then derive the optimal action by taking a greedy action with respect to the QSA function to maximize the QSA. Whereas for policy-based IR, you are directly optimizing for the action without learning the value functions first. So we in our project, in our lab, we are using DQN, which is a form of Q-learning, a form of value-based IR. So this is the overview of IR algorithms, model-based with known MDP, and a model-free with value-based and policy-based, and also a hybrid approach of actor critique, which is a combination of value-based and policy-based. So a Markov decision process. So it's the key attribute is that the next state only depends on the current state, not on the past history. So given the present state, the future and the past are independent. So given by this equation here. So starting from, let's say, time 0, you have action 0, state 0, and action 1, state 1, and so on until current state, ST. So now the next state, ST plus 1, the probability of next state is going to be another, the distribution of the next state is only dependent on my current state, ST, and current action, AT, within while in ST. Not dependent on the ST minus 1, ST minus 2, all the way to S0. So the Markov property is very important in simplifying the problem. So it enables all the algorithm in reinforcement learning. It's the foundation for all of IR. So for driving task, if you define the state as the vehicle position, the Markov property is not satisfied, because the next state depends not only on the current position, but also on the velocity and acceleration. But if you redefine the state as vector, x position, velocity, and acceleration, then it satisfies the Markov property. So your next state's position, velocity, and acceleration is fully determined by your current state position, velocity, and acceleration. So you may ask, why not go further? Why not x triple dot? That's a jerk. Why not x 4 dots? So well, there's an implicit assumption here that the x triple dot, the acceleration here stays constant from here until the next time step. If it doesn't stay constant, if the acceleration changes, then you do need to have x triple dot, the jerk, to describe the change of acceleration. So for a first order approximation, because if the time step is short, we can approximately view acceleration as being constant, so that we can stop at x double dot in the state definition. So for if you're mapping from a camera image to a driving action, from pixels to steering and brake, then you may use the current snapshot of the front camera, the current image as your state, and map from that state to the actions with a single feed-forward convolutional neural net. So that's the approach taken by NVIDIA's PilotNet. But it may not be the Markov property may not be fully satisfied. That is, your future, the future state may be dependent on the recent past history of the past, maybe a few milliseconds or a few seconds. So to be more accurate, to have higher performance, later work by Waymo's Chauffeur-net actually uses a history of past and video frames as a state to capture more dynamics, to make the Markov assumption more accurate. So here's a small example. With a single state and two actions, left and right, both returning to the same state. So notice the third alternative. If your policy definition is to alternate between left and right, so that is not a valid policy, because the policy is dependent on the history of actions, not on the current state. So it doesn't satisfy the definition of MDP. But if you redefine MDP's extended state to include not only the last action, but also the not only the current state S, but also the last action, then you can have this valid policy. So if the state is a tuple of S, comma, last action of left, then your action is right. If your state is a tuple S, comma, right, then your action is left. So then it's a proper MDP. So you can always redefine your state definition to make it satisfy the Markov property. So this is just an example MDP with the states, and so this is a non-deterministic environment. That is, with say you're in state S1, you take action A0, then it has a 70% chance of going into S0, and 20% chance of going into S2, and 10% chance of going back to S1. So the environment is it's uncertain. So So that's one example, MDP, reward function. Reward function is the most important hyperparameter, you can say, in reinforcement learning. So because the agent is trying to maximize its cumulative reward, whatever definition you give it, it'll try to maximize that. It doesn't have any other common sense. So reward function is the only communication mechanism you have with your agent. So you must define it to reflect your true intentions. So here is the example reward function for autonomous driving. So you can have a weighted sum of its heading angle, cosine heading angle. That is, it'll try to maximize the cosine theta, which is to minimize theta, to try to make the car heading straight on the track, not make the theta close to 0. And also you are trying to minimize the CTE. That is, you're trying to keep the car in the center of the track. So in our project, we only care about the CTE. We did not care about the heading angle. So you can add it to the project if you like. So actually, the Twiddle, simple little Twiddle function we saw before, actually is a form of policy iteration, policy gradient IR method. So it's trying to maximize the policy in the form of PID controller parameters. And by searching in the policy space of different PID P, I, and D, 3 parameters, a controller gains is trying to maximize its cumulative reward. So here's Amazon Deep Racer. You can, if you like, you can create an account in the Deep Racer system and play with the IR algorithm in that environment. So they ask you for a credit card number when you register, but they only charge you after you use the system for over 10 hours, I think. So reward functions can get very complex. We saw an example before. So yeah, penalizing too much steering and trying to stay close to the center line and so on. So when deep learning started, people are saying that deep learning is replacing handcrafted algorithms. So instead of designing the features by hand, like in traditional computer vision, you are learning the filters with a lot of data automatically. So you are eliminating human ingenuity from the software development process. But people are also saying that for IR, you are replacing feature engineering with reward engineering. So the reward function is a new handcrafted part that you have to write by hand. And you see all these numbers, 0.1, 0.25, 0.5. These are all heuristics you tune with trial and error. There's really no rigorous mechanism for setting these parameters, because for a neural network, the weights can be trained by backpropagation because it's differentiable with regard to the error function. But for these reward function parameters, these are not differentiable, so you cannot train it with backpropagation. So you have to optimize them by hand. So MDP, the search tree shows that from state S, you take an action, and environment gives you back a new state S prime and a reward. So in general, both the policy and the environment are probabilistic. That is, policy is probabilistic with a distribution over possible actions A from state S. And environment is probabilistic. That is, if agent takes action in state S, environment gives probability distribution over the reward R on next state S prime. So for example, the robot example, if the robot goes forward, the wheels may be broken, maybe not working so well. So it may go forward with 90% probability and go left with 5% probability and go right with 5% probability. So that's the environment outside of the control of the agent. And the agent may have a probabilistic policy, a stochastic policy. So especially for some kind of game environment, stochasticity is important. For example, if you're playing the game of rock, scissors, claws, it's important to have a stochastic policy, right? If you have a deterministic policy, you always lose. So the discount factor is designed to discount the future reward. So the future cumulative reward is the sum from t equals 0 to infinity, the discounted reward at every step. So the further away in the future, the more discount you apply to the reward. So the discount factor can be viewed as in another way. That is, at every time step, you have a 1 minus gamma chance of ending the process. So if the gamma, the discount factor is close to 1, then you almost never end the process. So if gamma is equal to 1, you always continue running. So it's an infinite horizon problem. You never finish. So if gamma is close to 0, then you're very likely to finish, to end the episode at every time step. So the gamma is determining effectively your horizon length. So here's the example of gamma equals 0.5. That is, at every step, you have a half chance of finishing the episode and a half chance of continuing. So therefore, at the current time step, you get a reward of 1. And then at the next time step, your reward will be only so suppose your reward sequence is 1, 2, 3. Then the next time step, your reward will be discounted by gamma, which is 0.5 times 2. At the next time step, your reward is discounted by gamma squared, which is 0.25 times 3. So you can think of the agent as having a 50% the chance of dying tomorrow. So if you give it $2 tomorrow, it's just worth $1 today. Because when it dies, the reward means nothing to it. So in this figure, I modified the slides this morning. So please download the latest version. So the agent is in a one-dimensional grid with the action left or right and exit, which is available only in exit state E. So in the left, the optimal policy is always to move west. if the gamma is 1, there's no discount. Then it'll always seek the state with the highest reward, the state A. So from state D, the reward of going west is 10, gamma cubed times 10. It takes 3 steps to get to A, so it's gamma cubed. Whereas if it goes east, then it gets a reward of 1. So the gamma, its reward is gamma times 1, which is equal to 1. So if a gamma is 0.1, then the optimal policy is this. So if you're in state D, then the reward from going west is gamma cubed times 10, which is 0.01, less than the reward from going east. Whereas if you're in state C, the reward from going west is gamma squared times 10, which is 0.1, whereas going east is gamma squared times 1, which is 0.01. So from C, the best action is to go west. So you can calculate the discount factor gamma for when the optimal action say D is equally either going west or east. So that is gamma cubed times 10 is equal to gamma times 1. Then gamma is 0.32. With this discount factor, the action at state D is it doesn't matter anymore. Left or right, east or west, the cumulative reward will be the same. So this is the big picture. I will not. I will actually play my last year's video for this part. Understand it right now, but I think you should understand it after I finish my lectures. So high level, the task can be prediction, where you compute the value function for each state for a fixed policy pi, or control, that is, you're trying to optimize the policy to find the pi star. And you may have algorithm with known MDP that's a model-based planning. And then you have these series of methods: policy evaluation, policy iteration, value iteration, Q-value iteration. And then for unknown MDP, then it's model-free. You need to use sample-based method, like Monte Carlo learning and TD learning and Q learning. So in this lecture, I will discuss this column here with known MDP. So with known MDP, we can use dynamic programming to solve MDP and find the optimal value and policy. So here's the Bellman expectation equation for state value function and for action value function. State value function is the expected value starting from state S and following policy pi. So it has expectation over actions, expectation over the reward and next state, current reward, and gamma times next value function v pi s prime. So it's expectation over policy pi given fixed policy pi, a big RT, which is defined as expected value at current time step t for typically for simple grid like problems, small games. For each state, we associate a reward. So if you enter the state, you get a reward. But in general, the reward may be dependent on the S prime. So from the same S and A, depending on different S prime, you may get a different reward. So that's a general case. But most cases in this lecture, we only have a single reward for the same state action. So this expectation typically it just means RT, big RT is equal to small r. But in general, it's an expectation over all possible reward at next state. So it's expectation over pi, the big RT, current reward at time step t, plus the gamma discount factor times the v pi of the next state, st plus 1. So the big S is a random variable with probability distribution. Small s is a particular state. And then you have the Bellman expectation equation for action value function. That is Q pi SA. That is the expected value starting from state S, taking action A, and then thereafter follow policy pi. So you first you take action A, and then you follow pi. So it's equal to expectation over policy, the current reward RT plus gamma v pi st plus 1, except the conditional probability has on the right, on the condition part, you have st equals small s and at equals small a. That is at the current time step, you take an action that's specified. And then in the future, you follow the policy. So the relating these two, v pi s is equal to a sum over action, the policy pi a given s times the q value function sa. And the q value function is can be written as the expectation over r and s prime, the current reward, and the gamma times v pi s prime. So that's the Bellman expectation equation. Bellman optimality equation. If you compare these two, okay. So if you compare these two, the only difference is you have a max over A for V star as the optimal value state value function, and max A prime Q star here for the optimal action value function, as opposed to the expectation over A for the Bellman expectation equation. So Bellman expectation is taking the expectation over all possible actions to calculate the value function, whereas the Bellman optimality equation is doing a max to find the optimal value functions. So if you write out this recursion, so the notation here is slightly different, but you get the idea. So the value function from S is argmax of A1. From S1, you take action A1,
plus gamma times the subsequent next state S2, and you have a transition probability. This transition here is corresponds to the notation above as P R S prime given SA. And then inside you have a max A2 and the next state S2 and action A2, and then gamma times the next state S3 and A3. So it's an infinite nested recursion. And if you cut the recursion this way, you have the Q value function. If you cut the recursion at a different point, you have a V value Bellman optimality equation. So relating the V star and Q star, you have V star S is max A for Q star SA, and Q star SA is expectation over R and S prime of R plus gamma V star. So this can also be seen from this figure here. So V star S is max action over Q star SA. So inside of this is the Q, and then you take the max, you get the V. Over max over A, you get the V. And starting from V, to get Q, you need to do more. You need to add up the current reward and the gamma times the future reward. So I would highly recommend you to stare at this picture for an hour and memorize it in your heart. So backup diagrams are very helpful in understanding Bellman equations. So look at, you can think of the big green circles as the action, as the agent in state S, with either a expectation for a fixed policy or a maximum for optimal value and policy. So at this state S, the agent can take an action A based on policy pi A given S to reach this blue state. The blue state is a so-called state action node. So it and then it's the turn of the environment to play the other hand and provide the agent with the reward R and the next state S prime. So this blue state is never is not a real state. It's more of a helpful construct to help you think of Bellman equation. So the real state transitions from a green to green, but it divides up the transition into two parts. One is from a green to blue, where the agent has the initiative and takes an action, and from blue to green, where the environment has the turn to take to give the reward and move the agent to a new state. And the backup diagram means that when the Bellman equations are backing up from bottom to top. So it's better if you look at the backup diagrams along with the equations. So for example, let me do a temporary move Bellman optimality for V star. So so let's look at this equation here. So from V star S prime, this guy, you multiply by gamma and add the reward R, you come up to the and take expectation over all possible reward and next state. So whenever you have no mark here, it's expectation. That's this part. And then you go up and take a max to get the V star S. So that's how you back up from V star S prime to derive V star S in this backup tree. And for Bellman expectation equation, the only difference is that now you have an expectation here, not a max. So for the Q value functions, you have a different view. Now you're starting from SA state. It means that you have already taken an action or decided to take the action A. Now you're just waiting for the environment to give you the next state S prime and the reward. And from this point, you can do a backup from Q star S prime A prime. You can do a max over A prime, and then back up. That's the expectation over here. That's the expectation. And then you get the Q star. Similarly for the Q pi, and both levels are expectations. So the agent only has choice of different actions for the state from the state nodes, that is from the big green nodes. And then from the blue, at the blue nodes, the environment has the initiative. The agent loses control at this point. So therefore, the agent can take a max to pick an action that maximizes the expected reward. But at the blue node, it's always expectation. The environment is not under our control, but our action is under our control. So that's why you may have max for the state nodes, but only expectation for the state action nodes. So any questions on the Bellman equations?
No question, but maybe I can take some time for the lab. So,
yes. Yes.
There's no hurry, but.
Okay, so last year's lab was different from this year's, so we'll skip this part. So in the video, I discussed the Bellman equations. So Bellman expectation for computing the value functions for a given policy pi, and Bellman optimality equations for computing the optimal value functions for any action. So the only difference between them is that for Bellman expectation equations, you have expectation sum over a pi a given s is really expectation over the possible a's. Whereas here we're taking a max over all the possible actions. So the backup diagrams are very helpful. Whenever you encounter MDP, you always try to draw the backup diagram to help you understand it. So from a state S, the big green state, the agent takes an action, and environment takes another, gives you a reward and next state. So the agent has control in its action. So that's why you can take a max over all the actions. So you can choose the action that maximizes your Q value function. Whereas from the blue node, the agent loses control, and the environment can give you back a new state and a reward. So if you look at the backup diagrams for the, if you start from the blue nodes, then you have the Q value functions backup diagrams. So it's just the, so really all these backup diagrams are very large or infinite trees of the that we saw before, for the NDP behavior. You have a infinite or very long, very large trees. So if you are viewing the tree from starting from a state, you have the backup diagrams for the V functions. If you're viewing the tree starting from a state action node, the blue node, then you have the Q Bellman equations. So the QSA contains strictly more information than VS. So given Q star SA, the optimal Q value function, the optimal policy is a simple greedy policy of argmax A. So take the A that maximizes the Q star. So you can always go from Q pi SA to a V pi S, or from Q star SA to V star S. From Q pi SA, you take expectation over all the actions, expectation over the policy. So the pi S A given S can be viewed as a probability distribution of the actions for the current state. So sum over the A is expectation over all the possible actions. And for the V star, it's a maximum of A or for the Q star SA. So and with a known MDP, that is, you know the transition function of the environment from the state and action, taken action, you get the reward and next state S prime. Suppose you know this P function, so that you know the environment. So it's a model-based method. Then you can go from V pi to Q pi by this equation. So that is you get the reward, and you take expectation over all the possible next next state S prime. And also you can go from V star to Q star by this equation. So you take expectation over all the possible next states.
I have a question there.
Sure.
This sigma sign is also over all R's, not
Yeah.
only S prime.
Yeah, I think that's probably my typo. Yeah, should be over all the next states.
Yeah, I was surprised if you could select the R's, so to say.
Yeah. Good catch. So you should look at the backup diagrams for these equations. So yeah, from Q, you can always get the V's. Because this is from the blue node, you can always back up to a green node. Whereas from the V, you cannot always get the Q's unless you know the MDP. That is, from the green node, you cannot always get back to the blue node because the transition, the MDP, if it's unknown, then you do not know how to take expectation over this probability distribution P R S prime given SA. So this environment MDP must be known if you want to back up, if you want to derive a Q at the blue node from V at the green node. So with the unknown MDP, then you cannot go from V pi to Q pi or from V star to Q star. So for the policy evaluation, it's also called the prediction problem. So you're trying to predict a value function for a given policy pi by solving Bellman expectation equation for the state value function. So so V pi, let me see. Q pi, yeah. Sorry, I have this typo. So V pi, this is the Bellman expectation equation. So you're taking expectation over the policy pi, and then the state, the reward at the next, the reward and gamma times the next state value function. So if you write out this equation for all the states, then you have a set of linear equations that can be solved efficiently for small systems, but not for larger systems. So number of unknowns is equal to number of equations is equal to the number of states. We'll see an example later. So if you have a deterministic environment, that is the environment, there's only one possible there's only one possible RS prime for a given SA, then we can simplify the Bellman equation. Well, with so the Bellman equation in general is the sum over A, the pi A given S and Q pi SA. And Q pi SA is equal to the expectation over S prime reward plus gamma times V pi S prime. So if you get confused, always look at the backup diagram. It will help you understand it. So for a deterministic environment, you can simplify this equation into this. So this capital R SA denotes reward is specific to the state SA. S prime is gone now in this form because S prime is there's only one. You don't have to take expectation over it. Plus gamma times this guy. So essentially the sum over S prime can be removed. Similarly for the Bellman optimality equation. So here's a toy example of a grid world. So let's work through it. So this is a simple grid with 4 states. In each state, you have 4 possible actions: left, right, up, or down. So the environment is deterministic. So taking an action A always moves to the next state in the moving direction unless it is blocked by the walls. Then it stays put in the same state. So discount factor gamma is 0.7. So the random policy, so we're doing policy evaluation. So we're given the policy we're trying to evaluate its value functions. We're not trying to optimize the policy here. So the random policy says the agent in any state A, B, C, D, it takes a random action, left, right, or up or down, with probability of a quarter each. So the Bellman expectation equation for the deterministic environment in the last slide is this. So it's V pi is equal to expectation over A, the Q pi SA, and Q pi SA is equal to reward plus gamma times V pi S prime, the next state. So V pi A, at A, you have 4 possible actions. So that is pi left given A is 0.25. Pi right given A is 0.25. Pi upper, pi up and down, each is equal to 0.25. So every pi is 0.25. That's this term here. And the Q pi SA can be written with this equation here. So if you're in state A, you're trying to go left, because the left is the wall. So you cannot move. And you go back to A. So, and the reward is 0. So here, reward 0. Plus the discount factor gamma 0.7 times V pi of A, because A is the S prime. It's the next state. It just came back. It cannot move anywhere. So that's this term here. So Q pi A left is equal to 0 plus 0.7 times V pi A. Similarly for Q pi A up, because up is also the wall. But if you're going right, you can get a big reward of 5, plus 5 here. So you get 5 plus 0.7 times V pi B, because it moved into S prime, which is equal to B. And if you go down, you have a reward of 0 here. And you have moved into a new state C. So the reward is 0 plus Q pi AD is equal to 0 plus 0.7 times V pi C. So these are the instantiations of this Q pi equation. And if you plug in these q pi's into the v, you get this expression here. So v pi a is equal to this term for the left action, this term. So this is a combination of the left and the up actions. And then this term is for the right action with the reward of 5. This term is for the down action. So this is how you get the equation for v pi expressed in terms of v pi a, v pi b, and v pi c. Similarly, for b, you can calculate this equation. So for now, if you're going right or up, you get stay in the same state b, but you get a pretty big reward of 5 here, plus 5. But if you go left, you go into a with reward of 0, or you go into d if you go down with reward of 0. Similarly for v pi c and v pi d. So finally, you have 4 equations and 4 unknowns: v pi a, v pi b, v pi c, v pi d. You can solve to get this solution. So that is your v pi value function for the random policy. And once you have the v pi's, you can solve for the q pi's with a simple arithmetic. So you can always do it the other way. You can write out all the q pi equations. That is 16 variables and 16 equations. You can solve for the q pi variables and then derive the v pi's. That's fine too. But solving for v pi's is simpler because you only have 4 unknowns and 4 equations. So the backup diagram here, I'm too lazy to draw the actual backup diagram. I just show the branching factor here, that from state S, you have a branching factor of 4. That is, you can take one of 4 actions. Whereas from a state action node, the blue node, you only have a 1 branching factor of 1. That is, you only have 1 possible next state for a given state action pair. So any questions on this grid word example? Okay, I think it's time for a break. Let's take a break for 10 minutes. So I got a message from a student that it is appropriate to sum over the reward. Let me look for that. 64. Where's that? Okay, so it is sum over the reward and the next state. So
Yes, sorry, it was my confusion. I just it looked a bit strange, but you arrived in different S prime and get different R's, even if you arrive in the same S prime, of course. I was thinking wrong there.
no, but if you're getting to a given same state as prime, why would you sum over R? I mean, the same state as prime should give you the same reward.
No, the reward can be stochastic as well. Sometimes when you move into S prime, depending on, well, the reward might differ.
No, look at this backup diagram here. So if you go into S prime here, you get the reward R. If you go into S double prime here, you get another reward R prime. So the reward is associated with the S prime. If you sum over S prime, you don't have to sum over R anymore, right?
Yeah, so but I was thinking that you might get different rewards. Sometimes you're lucky and sometimes less lucky. So getting different reward values.
I think what this means is really if you look at the probability distribution of P as prime R, comma R, then R is fully dependent on S prime, but you still sum over it, so it's equivalent to summing over S prime only.
But couldn't be like stochastic paths from S to S prime, several ones giving different rewards?
No, no, it's a tree, so there's only a single path, not a graph from S to S prime. Yeah. So let me dig into it a little more. I think they're equivalent. It's just a different way of writing the equations.
Yeah. But for me, it feels, as a programmer, it feels strange because these are the outcomes of selecting different actions. So how do you write code that sum over all possible S primes? It is more the result of taking an action in S.
Yeah, so this is expectation because the P, all the P's sum up to 1, right? Because it's a probability distribution.
Yeah, you know these P's. Yeah, that's right.
Shongo,
yes?
I'm not sure if it's only me, but I can't hear you clearly, actually.
Oh, sorry, I didn't have my headset set up. Okay, yeah.
Thank you.
Thank you, Cassie. I didn't hear him either so well.
Yeah, so just to reiterate, the question of whether you sum over S prime of comma R or sum over S prime only, really I think they're equivalent because R is fully determined by S prime. So the same, the two are the same. Yeah. Okay, so So this is the example where we know the MDP, we know the policy, and we write out all the Bellman expectation equations for all the VPI VPI for every state. Then we have 4 states, 4 variables, and 4 equations. We can solve for the VPI variables and get our value functions down here. So also we can get the QPI SAs. So this MDP is fully solved for policy evaluation. So if the number of states are too large, it may be too expensive to solve the set of linear Bellman expectation equations. So that is, if you have too many variables, thousands or tens of thousands, you may run out of memory. So in this case, you can use iterative policy evaluation and solve the recursive Bellman equations with iterative updates. So that is, you iteratively update your VKS from your previous iteration, VS is equal to Bellman equation VS prime, and you iterate a k's iteration number and until convergence. So here's the pseudo code. So you have a small threshold of theta. So every time you perform an update, you calculate the delta. That is the difference between the previous iteration's v value for state S and the current iteration. So if it stops change, if it falls below a threshold theta, then you say the VS functions have converged, and you stop the iteration. So for faster convergence, you can use in-place updates. So you update a VKS using the value of VKS prime that has been updated in the same iteration, instead of VK minus 1 S prime from the previous iteration. So in the Bellman equation form, you have this this form here. VKS is updated by applying the Bellman equation to a VK S prime instead of VK minus 1 S prime. We'll see an example later. So here's an example of iterative policy evaluation. So this is a grid world with 2 terminal states on the 2 corners, with VS equals 0 there, and reward R minus equal to -1 for every transition. So agent is punished for delays before reaching the terminal state and ending the episode. So you can think of the agent as having a very painful life. He just wants to die as soon as possible by going into one of the terminal states. The longer he lives, the more he suffers. So the discount factor is gamma is equal to 1. So there are 4 possible actions in each state, up, down, left, and right. So environment is deterministic. So as usual, if the action would move the agent off the grid, it instead leaves the agent in the same state. So this is the definition of the MDP. So the policy evaluation is based on the Bellman expectation equation for deterministic environment. So initially, all the v values are initialized to 0. So for the first sweep, we perform the update of the v pi s. So from every state, you have the policy is random. So in 4 directions, each one has 0.25 probability. So and then because every state has a value function of 0, it will reward a -1 plus the value of the next state, which is equal to 0. And this holds true for all four actions. So everywhere you move, you get a reward of -1, and you get a next state value of 0. So the 4 terms are the same. So sum up, you get -1. So this means that for all the states, except for the terminal states, the v pi s is equal to -1 for the first sweep. It's not converged yet. So, and then for the second sweep, for the states marked -2, these states, you can see that if you anywhere you move, you get to a new state s prime with vs prime equal to -1. So that's this 4 terms, all equal to -1 the reward plus -1 the next state's value function. And also every action is equal probability of 0.25. So you get the these states have the v pi s equal to -2. Whereas for the special, the 4 states marked -1.7, you have, say, this state. So this guy. So if you move left, you get reward of 0. So this will be left. If you move top, right, or down, up, down, or right, you get a -1 for the next state v s prime. So if you sum up, you get -1.75, which is approximately 1.7. So as you can see, now these 4 states have a new value function of -1.7 due to the influence from the terminal states, 0. Now look at the third sweep. For states marked as -2.9, these 2 states. So look at this equation here. So suppose you are starting from this guy, -2. So if you go up or go left, you get -1.7 and -1.7. If you go right or go down, you get -2 or -2 for the vs prime. So the sum is -2.85 or -2.9. So for this stage here, you have go left, you get 0. Go right, you have -2. That's this guy. That's the previous iterations v. Go left, you have 1.75, and go down, you have -2. Yeah, I have a little bit of inconsistency, so 1.75. So you can see that as you go through increasing number of sweeps or iterations, the influence of the terminal states gradually spreads through the entire grid. So initially, only these two states are affected by the terminal states with value 0, and gradually it affects more and more states. So this grid world, if you perform the iterative policy evaluation for many iterations, it will gradually converge. So for the left column is the sequence of approximations of the state value function Vs for the random policy. The right column is the sequence of greedy policies corresponding to the value function V pi s estimates. So at this initial stage, all the actions are equally good, because everywhere you see, you have a value function of 0. In this case equals 1 iteration. Now, in this state here, you should go left, because then you go into the terminal state and get a Vs prime of 0. So you die earlier and end your suffering earlier. So for k equals 2, so look at this state here. So if you go up or left, you get a minus 1.7 as the Vs prime. If you go right or down, you get a -2. So the greedy action will be go up or left. So as you go with more and more iterations, you will reach a state of this. So this shows the greedy actions for the value functions in this k equals 3. So as you have more iterations, 3 to 10 to infinity, the value functions gradually converge very slowly. So as you can see, as to 10 and to infinity, the value functions keep changing. But it eventually converge to k equals infinity. This is the final convergence. But the policy has converged, stabilized long before the value function stabilizes. So k equals 3, the policies are the same as k equals 10 or k equals infinity. In fact, this is a common phenomenon that the value functions will converge very slowly, but the many future iterations of the value functions do not affect the policy anymore. So the policy converges very fast. That's why policy iteration has the advantage of policy-based IR policy updates. For the model-free case, policy updates is very much more efficient than value-based learning.
Excuse me?
Yes?
Is there any way to deterministically decide when optimal policy is reached?
Well, you cannot, because you can never be sure that if your policy is going to change after the next update of your value functions. So in practice, it often stops changing way before value functions stop changing. But in general, you can never be sure. So yeah.
Because you also mentioned in some of the previous slides, or just showed that we have some thresholds which is used to decide when to stop iterations. So where is it?
Yeah. So the threshold is really a heuristic set by the designer. So the value functions, if the iteration, the change in the value function for a given state from previous iteration to the current iteration does not exceed the threshold, you stop iterating. But in here, you can see that from k equals 3 to k equals infinity, the value functions change a lot, right? So minus 2.4 to minus 14, minus 3 to minus 22. So this is really a large difference in the value function for a given state across different iterations. Yet the policies have long before stopped changing. So
More question. Does anybody try, or I'm not sure whether this is used in practice, but anyhow, could you just check, look at the policy change? If policy doesn't change, it doesn't matter what values are for some number of iterations, then you stop. Or
yeah, in fact, this is a good heuristic, but sometimes you can never be sure that, say after 10 iterations, your policy has not changed, but you can never be sure that at the 11th iteration, your policy may change, right?
Yeah,
so,
but just the question is like, I'm wondering when we are using, because in the algorithm, it's shown that we can use threshold, but it's not mentioned that we could look at policy change. So instead of threshold, or maybe some combination.
So we will discuss the generalized policy iteration in the
Okay, then I can wait for it. So it's like you can continue.
yeah. So yeah. So let me clarify a little bit. So for this slide here, we are always using a random policy. So let me try to clarify. So for this example, we're for fixed random policy. We're doing this for a fixed random policy. Whereas for this guy, the policy Figure 4.1. So we have determined the value function v pi for an arbitrary deterministic policy. Then we like to know whether we should change the policy to a chosen action A not equal to v pi s. So we know how good it is to follow the current policy from S, but would it be better or worse to change to the new policy? The way to answer this question is to consider selecting A in S and thereafter follow the existing policy pi. So this is one would expect it to be better still to select A every time S is encountered, and that a new policy would in fact be a better one overall. So so this is a policy improvement theorem. That is, if you have any pair of deterministic policies such that for all S, Q pi S pi prime S higher than V pi S, then policy V pi must be as good as or better than better than pi. So this is saying that suppose you have a policy pi, and if you take a new policy pi prime and take a single move with pi prime and then follow pi afterwards, then policy improvement theorem says that if that gives you a better better value function, then that policy pi prime is a better policy. So I really should make this copy this part into the slides. Somehow skip this part. So
just one thing, but
sure.
This is explaining when policy changed, but when it's not changing after iteration, then it's like you can't estimate because there's no change.
Yeah. So so policy improvement will be discussed next. So this slide is saying that if you take an action following the arrows in the figure, and from then onwards, you follow the original policy, the random policy, then the new policy of the current action plus the original pi, it will be better than the following the original pi from the start. So let me clarify this. Let me see. Okay, so let's look at this particular value function table in here. This guy. So so this is the value function for a random policy, uniform random policy, all actions equally likely, right? So if you are in this state, so the uniform random policy says you can move in all 4 directions with equal probability. And then you will get a reward, cumulative, your value function cumulative reward will be minus 2.9. However, if you're smarter and take the left action in this state and then follow the uniform random policy, your cumulative reward will be higher than if you had followed uniform random policy from the start. So from this uniform random policy, you have 4 choices. And then, but if you take the optimal action of going left, and then so in the original, at every stage you have 4 choices with equal probability. That's your uniform random policy. But if you're smarter and you take the action of left at the current time step, and then in the future you follow the uniform random policy forever, then your V will be higher. But the V is not calculated here, but it's just showing that for the given value functions here, the optimal action should be this. But the action is not actually used in calculating all the values in the left table. The left table is only for uniform random policy. But for the left table, you can take an optimal single step based on the value functions. So maybe we can clarify this further in the future slides. So policy iteration has policy evaluation as one step. So initialize all the value functions arbitrarily. Could be all zeros, could be all random numbers. And then you perform policy evaluation we saw before until convergence to within the threshold. And then you perform policy improvement. That is, you do argmax A for all the actions. You take a greedy policy with respect to the value function. So remember this part here is just a QSA written out in the form of V. So this part is QSA. So you're taking argmax A of Q for taking the greedy action that maximizes your QSA. And if your old action is different from your current pi-s, then the policy stable is false. So you haven't stabilized. Then if it's stable, then you stop and return the optimal value function and policy for that value function. Else, you go back to 2 to perform the policy evaluation of the new policy, and then improvement and iterate. So this figure shows that every time you take a greedy step of updating the policy, your Pt2 will always be better than your original policy. This is the policy improvement theorem. So simplified statement says that policy evaluation estimates the say value function v pi for some fixed policy pi by solving linear equations if you have a small system, or by iterative policy evaluation if you have a larger system and solving equations is too slow. And the policy improvement says that generate a new policy based on the newly estimated v pi. So since you have the MDP available, you can get the q pi from your v pi because you know the p. This is your MDP. So you can derive q from v. Then you just take an argmax a of the q. So this policy iteration illustration is that evaluation and then one step greedy update of the policy and iterate. So evaluation v equals v pi, and then pi equals greedy v. And if the pi has changed, if any s pi s has changed for any state, you go back and reevaluate the new policy v pi and iterate and iterate. So hopefully the amount of change, that is most states will have the v pi will have the pi s not change anymore. So the amount of change is gradually becoming smaller and smaller. Eventually, all states will have a fixed policy and will not change over the iterations. And then you have converged to the optimal value function and optimal policy. So let's look at this example of a policy iteration. Now you have a episodic MDP with terminal states in the upper left corner. Blue states are bad states with a large negative reward. So you should try to avoid these states. So start with uniform random policy. So the blue states have reward of -10, and other states have reward of -1. So the goal of the agent is to go into the terminal state as soon as possible, while trying to avoid the blue states. So intuitively, you can see the optimal policy is this. So in this state, it should go right. This state should go right. This should go up. Should go up. So you should learn this policy. But initially, you don't know that. So you start from uniform random policy. Initialize all the v's to be 0. So you run one iteration, policy iteration, you get this value functions for every state. So most states' policies are not good because they go towards the blue states. A darker color indicates lower valued states. So you can see that minus 238, minus 232. So it's expected because you are wandering around on the grid with no purpose. And your only chance of escaping the grid going into the upper left corner is by chance. So the farther away you are from the upper left corner, the less likely you'll wander into that state. So the more negative your value function will be for the random policy. And then after one policy improvement iteration, you can see the policies. So the change at this point, so minus 194. So if you go up, you get minus 129. Go right, you get minus 214. Go down, you have minus 217. So obviously going up is better. Similarly for these guys. And you can get a better policy than uniform random policy based on the value function shown on the left. So now for this policy, we do another round of policy iteration. We get a much better set of value functions on the lower right, lower left. But a few states policies still go towards the blue states. So in here, minus 12, you go towards this guy, minus 2. So that's a bad policy. So it's going left in the lower row. So it should go right. So now you perform policy improvement based on this value function on the left. You get policy improvement.
It's better compared to the policy above, I guess.
Yes, but why is it left and up?
Up
It
is
should
minus
be,
3, that is.
yeah, it should be up. So let's go forward. Okay. I see. Because the remember the blue states have minus 10 as reward. So if you go up, you get minus 10 plus minus 3, which is minus 13. Go left, you get minus 1. Yes. So so this, if you recall, the definition of the reward for the blue states is minus 10. For the other states is minus 1, right? So if at this point, if you go up, you get minus 10, minus 3. If you go left, you get minus 1, minus 12. So that's why you have an up arrow and a left arrow, because these two directions are equally good or equally bad. So that's why you have these arrows after policy improvement. So another round of policy evaluation based on this new policy. Now, based on these updated value functions, this guy's policy has changed. It should point right. because if it goes up, it has reward -10, -4. If you go right, you have -1, -6. So going right is better. The others stay the same. So another round of policy evaluation, you get a new value function here. And then this guy should go right based on the new value functions. So -13 on going up and -8 going right. So another round of policy evaluation, get a new value function, and then at this point, this guy has changed from going up to going right. Going up, -12, going right, -9. So that's a good sign because going right is the right is obviously closer to our intuition. And another round of policy evaluation, now the value functions have converged. That is a few further updates will not change it. But in general, it may not converge. Policy often stabilize long before value functions converge. And from this, you look at the greedy policies and stop changing. So this policy and this policy are the same. So now policy is stable. So we're done. So this is the policy iteration example. That is, you are iterating between evaluation and improvement. This improvement is one-step improvement until the V and pi have stopped changing. So any questions on this example?
For me, it looks it can get stuck in some kind of suboptimal situation if you don't use some exploration at all.
Well, this is not exploration because you're updating the value functions and policies for every state simultaneously in every iteration. So you're not like for a little agent going on some random direction. No, we're not doing that. We're solving the MDP because we know the MDP. This reward, we already know that. So we're solving for every single state.
Yeah, and you start with random as the first step, so then you kind of have an exploration state the first time.
In a sense, we are exploring exhaustively every state in every iteration.
Okay.
Yeah. So we're computing the value functions everywhere. Yeah.
I have one question.
Sure.
Seems like this is now completely ignoring threshold, like delta. It's just every step is going to next comparing.
No, we do have the threshold because that's in the evaluation step. So the reason we have these 232 or 214.3 here is because we had a threshold, theta somewhere. So we know when to stop. So in the policy evaluation step, we have the theta until delta less than theta, then we exit. Otherwise, we'll go for a very long time or never exit. So all these values are approximate. They're not exact.
Or it's not just only this is showing just this final state after the
yes,
iteration.
after
No.
it has converged based on the theta parameter. Yes. Obviously, if you're for this small system, actually you can just solve the set of linear equations instead of doing the iteration. Then you can get the exact answer. But in general, for larger systems, the linear equations are too large to solve. That's why you need to iterate. By iteration, you always get an approximate solution. How much approximation is allowed is determined by the theta parameter, the theta threshold. So here's another policy iteration example where the value function starting from all zeros, after fifth iteration, you get this. After 10,000 iterations, you get this. So the greedy policy based on the initial value functions will be uniform random. At this point, your greedy policy should be this, assuming that every state has the same reward. So you always point to the higher value function. And even though you have gone many thousands of iterations after the fifth iteration, the policy stopped changing. So the precise values of the VS are not necessary for computing the optimal policy with policy iteration. So for value iteration, you obtain the optimal value functions by solving the Bellman optimality equation for state value function. So notice you have the max A instead of expectation over A. And then after you have converged again with the threshold of theta, you can output the optimal policy by taking argmax of the Q SA. So the intermediate value function VS may not correspond to any valid policy. So generalized policy iteration says that so you evaluate given policy and then improve the policy by acting greedily with regard to its value function. And GPI is guaranteed to converge to the optimal deterministic policy pi star. So there are two special cases for GPI. One is policy iteration. That is, you perform policy evaluation for a given policy until convergence, and then you improve the policy to a new policy, and then evaluate the new policy until convergence, and then improve the new policy, and so on. For value iteration, you perform policy evaluation with a single iteration, and then improve the policy implicitly. That is, you're not so the policy is implicitly determined by the Q functions. So so policy iteration is slower per sweep and requires fewer sweeps. A value iteration is faster per sweep and requires more sweeps. So because for policy iteration, every policy evaluation step must iterate until convergence. Whereas for value iteration, you can think of every update to the Q star function with the Bellman optimality equation is one iteration of the generalized policy iteration. So you can think of every update to a Q star is one sweep. You can strike a balance between these two extremes with modified policy iteration. So you run policy evaluation for number of steps between 1 for value iteration and that needed for convergence of V pi for policy iteration. That is, you are running the policy evaluation not to convergence. So you forget that the theta threshold and just run it for 15 steps or 25 steps, and then do the policy improvement, and then go back to policy evaluation. So you reduce the policy evaluation overhead. So even so, this figure illustrates that. So you don't evaluate policy to convergence. Even so, this is still valid. You can still show that this will converge to the optimal policy and value function. This requires some proof. I think it's in the book.
I have one more question.
Sure.
Is convergence guaranteed?
Yes. For generalized policy evaluation, convergence is guaranteed. Policy iteration, value iteration. Generalized. So if both the evaluation process and the improvement process stabilize, that is no longer produce changes, then the value function and policy must be optimal. So the value function stabilizes only when it's consistent with the current policy, and the policy stabilizes only when it's greedy with regard to the current value function. So both processes stabilize only when a policy has been found that is greedy with respect to its own evaluation function. This implies the Bellman optimality equation holds, and thus that the policy and the value function are optimal.
Yes, but this still doesn't show that I'm just trusting you, but this just does. This is not showing that the convergence is guaranteed. It just says that if it is stabilized, then it's optimal.
That's true.
But you don't need to look at for it. I mean, I have to trust your word, so it's like it is a guarantee. And anyhow, you just showed that we could actually limit iterations, so we don't need to wait for the threshold, which can just stop after some number of iterations.
Yeah. So the point is that even if you do this, even if you limit the number of steps for policy evaluation to a fixed step instead of evaluation until convergence, the whole process of generalized policy iteration will still converge until optimal V star and pi star. So the book says that if this generalized GPI converges to a fixed V star and pi star, then this V and pi will be guaranteed to be optimal. And you're asking if this whole process is guaranteed to converge. I think it is, but I'm not very sure where to find the proof. Yeah.
I mean, it's okay. You don't need to spend too much time on it.
Sure. Yes.
It's more like I was worried. I was thinking like how it will be solved in the computers, and if it is stuck, like if there's no convergence, what we are doing then. But we can limit number of steps, and then that's not the problem anymore.
Yeah. So if you're worried about the convergence of the of this guy, then if you're worried about convergence of delta less than threshold, then you can limit the loop iteration to be a given bound. It turns out it doesn't affect the correctness of the algorithm. But if you're worried about the convergence of the whole system, the whole loop, then it requires perhaps additional information. I'm not presenting here.
It was more like I was worried that if whole system is not converging, then this particular step 2 is not going to stop any. But if we actually have it's less than threshold or the number of steps, then we'll stop at some point anyhow.
Yes. The best thing is that even if you have a fixed step, it doesn't affect the correctness of GPI. Yeah. So let me go back to the to this example here. So this example is discussed before the policy iteration. So this is part of the policy evaluation section. So the whole process is the uniform random policy. All these tables are computed based on the random policy, and the this policy, greedy policy here shown is only with regard to the current value function table. So we're not doing policy iteration here. Yeah, let me clarify. We're computing the value function for the random policy. So left column is the sequence of approximations of the state value function. Right column is the sequence of greedy policies. The policy is always the random policy. And we're just showing the current best action with regard to the current value function. So follow the greedy action. At the current step, then follow the random policy in the future, then it is I hope it's clearer. So in this example, we're not updating the policies. So the policy is always uniform random, but the arrows show that the one-step action, if you take it and then follow the random policy, is better than following the random policy from the current step. So this is kind of a hint towards the next section on policy improvement. That is, in the policy improvement example, you're actually changing the policy at every iteration until convergence. So that's the difference. Is that clear? Okay, so we will stop here. Okay, so see you next time. Anything to add?
No, it's just I'm saying thank you and see you next time.
Sure. Okay, goodbye.
Bye-bye.
Thank you. Bye.
Thank you.